It's 3 o'clock, so let's get started. So the midterm was due last night, and everyone did well, which is awesome. But the final will, if you do better on the final, it'll replace the midterm grade. So hopefully you can even raise your scores even higher than what you had there, which will be exciting. So any questions about the midterm and anything about that? Yeah.
Can you go over the changing the time and numbers to words? Because for some reason, test case number 2.
Is that's called the time and words? Yeah, that was.
That one was a little tricky.
I got the one wrong. I think you had to infer that you also need to do quarter from.
Yeah.
Oh, are you kidding?
Yeah. There's a small.
That's really really strange. Also, a problem that I had a lot was that I went because the way that I did it, I just did. I had a bank or what's it called, an array of words that just had 1 to 20, right? Yeah, and so I just indexed it at whatever, but it would go from 12 to 13 instead of 12 to 1 to 2. I don't know if you guys.
I got it as well. It wasn't really a problem for me. I just made it do array of hours and added one at the end of that. But then I actually did the quarter, but I guess I didn't do from. I don't know what I did.
Because it's like 1:15 is like a quarter or a quarter past. A quarter past 1. Yeah.
Yeah. So.
I knew it was quarter.
Yeah, each one of these you actually did need to implement. So like getting right on the time, like within, there's quarter after and quarter to. Yeah.
So wait, I have quarter past and then quarter to.
Yeah.
And then there's quarter from.
No, not quarter from. I misspoke. It's quarter past.
Oh,
Then why?
I had quarter past.
Oh, you guys did that?
Yeah.
I don't know why.
Well, we can look at your leaderboard. So,
I'm Chris.
yeah. Really? Okay. So minutes, a minute. Yeah. So you needed to differentiate 1 minute past and several minutes past. So that may be an issue there. So there's that off by 1 error that you need to check, as well as right on the 15 minutes and also on the 30 and right on the hour.
Yeah, something in the acronym output has to be like just perfect.
Yeah, the reason I included this was, although it's not really algorithmic in what we've seen so far, it's being able to solve a particular problem and just being able to handle a lot of test cases, because I know that there's a lot of details here. So that's why it wasn't as easy as some of the other ones. So.
I did quarter to. I did quarter past.
Yeah. And I don't know what the test cases are because this is HackerRank's one. Yeah. So every single little thing, every one of those, you had to implement correctly, as well as the one off by 1 things, like 1 minute to and 1 minute past. So it would be good that S on minutes really makes a difference. Because it has to. Well, it has to match exactly. So.
It's like that was my problem for a little bit. I didn't have the S, and then I did go back and change 1 minute.
Okay.
It's still just test case 2.
Test case 2, it does everything wrong. Yeah. It also may be a problem with changing from 12 to 1.
I also did take that into account.
Okay. Yeah, I'm not sure. I'll have to look into it. But it's always these little off by 1 errors.
It's probably some tiny little thing I spelled something wrong. So.
Yeah. Yeah. So any questions else on the midterm? Cool. So I liked how this went. It was super easy to do, so I'm thinking of making the final the same way. But just different problems. Yeah.
Actually, on the last one, can you show us how to optimize that? Because I kept getting timeout errors.
Oh, which one?
The Colette's.
The Colette's one?
Oh yeah, I keep on getting timeout for that too.
Yeah.
Yeah. This one is really, really difficult. So I don't have a solution here, but the way to do it is to store it as a dictionary. So and you store the previous computation, but there are some other optimizations. Like this problem is really, really hard for a lot of people. Like if you look at the actual contest where it is, I don't know what the percentage acceptance is, but it's probably around 60%. It's a low acceptance. Yeah, that's why I put it last. It was one of the hardest ones.
That was fun.
Yeah.
Until
It was fun until. Yeah, 56%. Yeah, yeah. So, in fact, I haven't even solved it yet to completion. So, let's see what my submission is. I just have wrong answers, but. But the input size really is huge. So, what some optimizations you can do, like one of the other ones is, let's see, there was another one which is kind of the same. I don't know where it is, but it's the longest palindrome number between that is a multiplication of two 3-digit numbers. And so what you could do is just actually do the computation, but the better way, because that runs out of time, is just generate every single possible solution right at the start before you even do test cases, and then just check in this set if it's there. So instead of actually doing the computation many times. It's not even storing previous computation, it's just, it's not storing previous computation, it's just doing everything right at once and then just looking it up right at the end. So, yeah, so that one is pretty difficult, but the main idea as a main optimization is use a dictionary for easy lookup in figuring out what the length of each one is. So you store for each number n the collat's length sequence for that particular number n. Then when you get a new number, you just look up in the dictionary. Yeah, so it's kind of like dynamic programming. You just save computation. But yeah, if someone, I think you can still access this. If someone can figure out, or at least be able to solve that, I would really love to know how you did. So maybe some bonus points in there too. But I would love to know how you can solve that.
Well, it could be like submit to get the difficulty change, because I felt like super special mode. You could get like 2 points on it. I'm just teasing.
Yeah.
Like I said,
yeah,
someone
no.
brought it up, and that's what threw me off. I was like, this is easy.
Yeah, that's no button.
Yeah,
That's
yeah.
the first problem that I
Yeah,
tried. I'm like,
yeah.
oh, this big person.
So obviously these are from other contests, right? And so the difficulty, the word difficulty corresponding to it, is not indicative of it. It's the points that were indicative of it. So like, I mean, advanced and easy, yeah, that are worth the same, yeah. I just put what I thought were the hardest ones at the end. So any other questions on the midterm stuff? Okay, yeah, so I'll have a final similar to this. Okay, so any questions on assignment 5? Any last minute questions while everyone's here? Yeah, so it's just analyzing the data set we talked about, I think 2 weeks ago now, and just answering some other questions about it, trying to analyze the data set. Okay, so I haven't finished making assignment 6, but I'll give you a little preview of what it is. It's essentially doing a little more on what we've been talking about, this P and NP stuff. And then, so I just give you a whole bunch of problems for which I would like to solve, and I want you to tell me whether it's in P or it's in NP or neither. Okay? So it should be pretty simple to do. And then just say why each one is either in P or in NP. Okay? So any questions on assignment 5 and this draft, assignment 6? Okay, so let's get back to the stuff. So yesterday we started talking about this topic called intractability. And what that is trying to get a notion of what problems are difficult and which ones are easy. Right, trying to figure out, maybe we may know that a problem is for sure difficult. Like we know for sure there's no easy algorithm to do this, no efficient algorithm to do this. But maybe we don't know, and it turns out we actually don't know for a lot of them. So maybe we can develop some heuristics as to why this problem may be difficult. And so we talked a little bit about what's a good algorithm, that kind of thing. And then we got into this motivational problem where we know shortest paths are easy, but we established that longest paths seem to be a lot more difficult to solve. We can verify whether a solution is correct in the same amount of time, polynomial amount of time, but actually solving a given instance instead of just verifying a particular solution, it seems a lot harder for the longest path problem. So we started talking about these two classes of problems called P and NP. So P is the set of all problems for which we can actually solve the instance in polynomial time in terms of the size of the input. And so what does solve mean? Well, if we phrase a problem in terms of a yes-no question. So we're given an instance and we gotta say, it has this certain property, like it's in this, the problem would say yes to this particular input, or it would say no to this input. So that's what we call a decision problem, right? We may phrase a problem in terms of, outputting the longest cycle in a graph. Like we could reason about how long that would take, but there are some issues that arise from that. For example, being able to figure out what the format of the output might be. You may say, I'm going to output a lot of data versus a small amount of data, right? So there may be some issues with being able to phrase a problem not in terms of a yes-no question. But if we phrase it in terms of a yes-no question, then we are unambiguous in our answer. It's either yes or it is no. So P, when we're given an instance to a problem, we are able to say yes or no to that instance in a polynomial amount of time. Okay? So we also established that not only could we solve a problem in polynomial amount of time in terms of the size of the input, we can also check if a proposed solution is correct to this instance. So as an example, let's say that I want to solve whether there's a triangle in a graph. So recall that a triangle is a set of three vertices in a graph for which they're all connected to each other. So it forms a triangle. So an easy polynomial time algorithm is enumerate all possible three choices of vertices, and for each one, check if they're connected to each other, if all edges are present. So it basically forms a three-clique. So we know how to do that in polynomial amount of time because we have n vertices for the first choice, n minus 1 for the second, n minus 2 for the third. Those multiplied together are approximately n cubed, and which is a polynomial. So we know how to do this in polynomial amount of time. But we know how to verify whether a certificate is correct, right? So my friend says, oh, I believe that of this instance, these three vertices form a three-clique, or they form a triangle in this graph. And I say, I don't believe you. So I take his certificate, and I say, are these three vertices part of the original graph? And then I verify that. And I say, okay, that's good, they're in there. And then I check, are the edges, all three of them, present in the original graph, right? Because if one of the edges wasn't there, then my friend's proposed solution is wrong, right? So therefore, I just need to check, are all three of those edges present in the original graph, which is easy to do. So therefore, I can verify whether a particular solution is correct in polynomial amount of time. But another way I can verify whether a solution is correct is just rerun the algorithm again, right? Because if I just rerun the algorithm and I come up with the same solution my friend did, we're already good. So I can either solve the original problem or I can verify whether a proposed solution is correct in polynomial amount of time. So that's what P is all about. But then we said, maybe we can look at more problems because like that longest path problem, maybe we don't know a polynomial timing algorithm exists, but could we still check if a proposed solution is correct? So NP is the set of problems for which we can verify a proposed solution correctly. And so N, in terms of NP, means non-deterministic. So obviously that means not deterministic, but what that really means is I am at a particular point in the computation, and a non-deterministic choice means if there's a way eventually for me to say yes, currently where I am, I will make the correct choice, right? So it's kind of what is called a lucky algorithm. It does always the right thing if there's a way to do the right thing, okay? But another way of phrasing NP is the set of problems for which we know how to verify proposed solutions efficiently. And so we just came up with a few problems which are in NP, figuring out whether there's a negative weight cycle, for example. We start with a vertex, and then we non-deterministically choose the vertices which either form a cycle or don't. And so at the end, I just verify whether all the choices that I made actually make a negative weight cycle. And then if they did, then I say yes. If they don't, then I say no. Pretty simple. But we can also verify whether a proposed solution is correct by just looking at the solution that I'm given. If it forms a negative weight cycle, then I say yes. If it doesn't, then I say no. Pretty simple. And then we have some other ones we talked about. So we wanted to establish the difference between P and NP, because this is one of those Millennium Prize problems that everyone's been talking about, and it's worth $1 million, so a lot of work obviously has gone to do this, to understand the difference between P and NP. So we might want to talk about how have people tried to separate these two, or tried to show that they're the same. So what we're going to do is we're going to try to develop some heuristics as to why they're different. And so we know that since every P problem, we can verify a solution efficiently in polynomial amount of time. And that's what the definition of NP is. Every problem in P is already an NP. So we know P is a subset of NP, but we don't know the other direction. So we don't know whether they're different. So maybe we want to figure out what would be the best choice for a problem to exist if they were different. Because if such a hardest problem existed and is outside P, then we just separated P and NP. If P and NP are different, then certainly the hardest one is outside P. So I kind of want to find what that such hardest problem is, right? That's my goal. I want to analyze the hardest problems in NP, the hardest ones for which we know how to verify a solution efficiently. So then we started talking about what's the hardest problem. So if we know an efficient way to solve this hardest problem, then everything that's less hard than it, I know how to do efficiently, in a sense, right? Because this hardest one is efficient, then everything else must also be efficient, right? So then now we're going to make this a little bit more formal. So any questions on what we've talked about so far? Okay. So the basic idea here is that if we want an efficient algorithm for a hard problem, then we want some way to convert it to an easy problem for which we know how to solve efficiently, such that the answer to the hard problem is the same as the one to the easy problem. So they correspond to each other. So that's the thing that we want. So that's what's called a reduction. And throughout your entire programming career, you've used reductions all the time, right? You've used code for which you didn't want to develop twice, right? So you wrote some algorithm that solved some problem, and instead of rewriting that algorithm over and over and over, you stuck it into some function, right? And then you use that function call somewhere else. You're using the solution of the existing algorithm to do some other solution. So that's essentially what a reduction does. A reduction is basically a way to convert instances of a problem into instances of another. But the key here is that we want to retain the answers to be the same of both, because if they were different, then there's no point in doing this reduction at all. So what I want here is that if the answer to the hard problem, or sorry, the first problem was yes, then the answer to the second problem, the one I'm transforming it into, its answer is also yes. If the original answer was no, the answer to the other one's also no. So it preserves the answer. So basically what this is transformation of one problem to another. Okay? So that's essentially what we wanted, right? We want a way of transforming all of these problems into this hard problem. Because if we can do that, then we can establish what the hardest problem is. So let's consider two problems, A and B. I'm going to call them A and B. If there's a reduction from A to B, I would call this A less than or equal to B. And I'm so sorry about the notation. This is what is used in the literature. Because I would have much preferred, like, say, an arrow or something, like A transforms to B, but this is what we're stuck with. So the way you should interpret this is, I have a particular instance of A, say like a graph, and I want to transform it. I apply something to this graph, and then whatever the output of that transformation is, it's an instance of B. So maybe, I have an example coming up, but essentially what I'm doing is I'm doing a transformation between two problems. Formally, we call this a function, right? It's a function that takes some input and produces some output. So as input, it takes an instance of A, and it outputs an instance of B. So, and that's another way of saying it. So there's instance W of A. If and only if I apply the function, the result is an instance of B, right? So it's just this, the if and only if preserves the answer. So if this instance is not in this problem A, like for example, a graph that doesn't have a negative weight cycle, right? The answer for if I apply the reduction would also be no, right? The answer is yes, if and only if the answer after I do the reduction is also yes. Questions on this? Okay. But of course, we don't want reductions that take too much time, right? Because I'm reasoning about P and NP, which take polynomial time and non-deterministic polynomial time. I don't want these reductions to take doubly exponential time, for example. I don't want them to take too long because, of course, the reduction can't be more powerful than the problems that I'm looking at anyway, right? Because that would be nonsense. So what I want to look at are reductions that don't take too much time. And of course, I don't want reductions to be more powerful than the actual class itself. So what we call a polytime reduction is a reduction for which it only takes polynomial amount of time to do it. So given a particular input, which has a certain size, if I can do the reduction in a polynomial in terms of that size, then I call it a polytime reduction. Of course, there are other types of reductions, both that are less powerful, some that are more powerful, but the one that's used most often is a polytime reduction. So, and we write this because less than or equal to was for arbitrary reductions. Because we reduced this to polytime, we abbreviate it as A less than or equal to with a subscript P to B. Okay? So, what I mean here is that the transformation applying this function only takes a polynomial amount of time. And so what will be really important in establishing a hard problem is this notion called polytime equivalent. So they're equivalent up to a polynomial amount of time. What does that mean? I can transform A to B, and I can also transform B back to A, right? There's a reduction in both ways. It might not be the same reduction, but there is one in both directions, okay? And so let's think about that polytime equivalence thing. So if I have two problems that are polytime equivalent, let's think about their efficiencies for a second. So let's consider problem A for a second. So either A runs in polynomial amount of time or it doesn't, obviously. So if A runs in a polynomial amount of time, what can I say about B? Well, also runs in polynomial time. What if A doesn't? Then B doesn't, right? So either both have efficient solutions or neither do. So if we can establish problems for which they are polytime equivalent, and we can have some other notion for which we can say they're the hardest problem in NP, then therefore these are the hardest problems in NP. Okay, because either they're right at the top of the NP hierarchy or they're all the way down in P. So there's this big separation that could take place. So that's essentially what we want to establish here. So the two problems we'll talk about are called Clique and Independent Set. So we know what clique is, right? So what's a clique?
It's part of a graph whose vertices all connect to one another.
Right, exactly. So it's a subgraph, or you can think of it as an entire graph for which every possible pair of vertices is connected to each other. So it's a complete subgraph. It's another way of saying it. Okay, and we'll get to independent set in a second. So a clique is a complete subgraph for which every edge exists. So obviously we're talking about decision problems, right? We can't just say find the largest clique in the graph because that's not a yes-no question. So we need to phrase this in terms of a yes-no question. But we kind of want to have that notion of finding the largest clique, right? So what we want here is we're going to phrase it in this way. So we're going to phrase this as an instance called, it's called an encoding, but don't worry about that. It's essentially we're given a graph in an integer k, right? And what I want to be able to determine is that G is a graph, and there's a clique of size at least k, right? So essentially this is solving the problem, essentially as a decision version, because I can just keep upping k until I get the largest clique in the graph. So let's think about just a naive way of implementing this clique, right? So what's a naive way of solving this? So I'm given this graph G and this integer k, and I want to determine there is a clique of size at least k. So what's a naive way of doing this? Well, really not naive, but at least brute force. Think of, oh yeah, go ahead.
I just look through every vertex and see if it's connected to all the other vertices.
Well, this k may be different than the number of vertices. Like, let's just think of the, if k were 3, right? So I want to figure out if there's essentially a triangle in the graph. So how did we do that?
Search through it until you find a vertex that has a degree of 2, as those two that it's connected to are also connected to each other.
Yeah, so I could just look through all vertices for which it has degree 2, but I'm talking about induced triangles. So I ignore the other edges. So it could have other vertices for which it's connected, but there's still a triangle over here somewhere. So it may not always work that way. The way that's kind of brute force is just look through every possible triplet of vertices. So I pick one vertex out of all the vertices, pick a vertex that's not that first one from all the other vertices, and pick a third vertex that's not those two. And then for all possible choices, check if they're all connected as a triangle. And then if they are, then I just found a triangle. So how would I extend this to at least k here? Instead of just looking through all possible triplets, I just look through all possible k choices. So n choices for the first, n minus 1 for the second, n minus 2 for the third, dot, 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 up to n minus k, right? So therefore, I just look through all of those, and then I check every single one of those k vertices is connected. If I did, then I found a clique of size k. But this says at least k, right? So what if there was one of k plus 1? And I'm just only doing k. Do I need to search the k plus 1? No, why? Right. If there's one of size k plus 1, then a clique of size k would be contained in this k plus 1 one. So I only need to search k here, right? So let's think of the runtime. I choose n for the first, n minus 1 for the second, dot, 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 n minus k for the last one, roughly. So what's the product of those choices? n times about n times about n. How many times?
N to the
Yeah, k. So the runtime is n to the k times the amount of time to check those vertices, right? So how many vertices I'm checking is k, right? And so I need to check k times k minus 1 choices in this k choice that I made. So I'm checking k squared order k squared edges in this k possible clique, right? So the runtime is n to the k choices times k squared choices for here, right? So wait, isn't that polynomial time? How large can k be?
as long as k is less than that.
What if it's n minus 1? It's that n to the n minus 1, that's not a constant. What about n to the square root n? Not a constant. Yeah, so unless k is a constant in terms of n, this is not a polytime algorithm. So that's one of the major problems for why we believe that this is not a polynomial time algorithm. We don't know how to check the higher values of k efficiently. For all the constants we know how to do, but we don't know how to do it in terms of n, right? Other than a constant in terms of n. Okay? So that's a way of brute forcing this problem in Clique. Okay? So an independent set, on the other hand, is the complement of a clique. So what do you think the complement of a graph is? We didn't go over this, but just looking at it. What do you think complement means?
Is it everything that's not
Essentially, yeah. So the complement of a graph is, if there was an edge there, it's not in the complement. If there wasn't an edge there, then it's not there. Right? No. If there wasn't an edge there, now it is there. Yeah, I think I got that wrong. So, complement of a clique. Well, a clique is a set of vertices for which every edge is present. So what do you think an independent set is? Yeah, a set of vertices for which none of them are connected to each other, right? So you just take every edge that was there, then remove them all. If there was a clique, then no edge is there now among those vertices. Okay, so that's what we call an independent set. And so you think, well, these problems kind of seem related, right? The clique is kind of the opposite problem, like the inverse problem of independent set. And so we're going to define an independent set of this way. G is a graph with an independent set of size at least k. And let's go through a brute force algorithm. Just look at those k choices of vertices and check if there's no edge present. If there happens to be one for which there's an edge there, then therefore that's not an independent set. So I move on to the next one. And if it turns out that there is no edge among those k vertices, then therefore I just found an independent set. And the reasoning for larger values of k goes the same way as clique. So is clique an independent set clear? Any doubts on this? Okay, so what we're going to do is we're going to show that we can reduce clique to independent set. So given an instance of clique, which is this graph G and an integer k, I can transform it in polynomial amount of time into an instance of independent set, a graph G and an integer k. So I'm going to be given this graph G and integer k, and I need to produce as output, because I'm doing a reduction, a graph G and also another integer. It might not be k, but I need to produce a graph and an integer. Okay? I need to preserve also the answers. So whatever was, let's just say that the answer for the input that I was given for clique was a yes. So therefore, whatever I produce as output must also be yes. If it was no before, it must also be no now. Okay? So we need to transform an instance of clique into an instance of independent set. And we also have to maintain, if it wasn't in clique, the result of whatever I do must not be an independent set either. So an idea here is that an independent set is the complement of a clique, because that's the definition. So what do you think is a good reduction that I can do? So I'm given this graph and this integer k. What can I do as a reduction? Well, if this graph I was given had a clique, I better produce a graph that has an independent set. If this thing does not have a clique, this thing does not have an independent set. Use the definition here. So what is a reasonable way of doing a reduction here? Well, I'm not actually finding independent sets or cliques. I'm just saying if there was a clique there, the thing that I'm going to produce has an independent set. If the thing did not have a clique, this thing does not have an independent set. Right? So what I want is to convert this graph into another graph such that the answers are the same. So what's a reasonable way of approaching this?
Maybe wherever there was an edge, take it out. Wherever there isn't an edge, put it
So what is that called?
in. Reverse it.
It's called complementing the graph. Exactly. So what we do is complement the graph. Well, let's think about it for a second. The graph that I'm given has a clique or it doesn't. So if it did have a clique, if once I do the complementation of it, of those vertices that did have a clique, none of them exist now. That's an independent set. If it did not have a clique, let's just look at every possible choice of where there could be a clique, but there isn't one. Over here, when I do the complement, one edge at least must exist among every possible choice. So this thing had a clique if and only if this thing had an independent set. Is that clear? Yeah, so essentially, if the graph had a clique of size at least k, then the complement has an independent set of size at least k also, just by doing this complementation, right? And the same thing goes for the opposite. So wait, I write here clique, polynomial time reduces to independent set. So we preserve the answer, right? It's yes corresponds to yes, no corresponds to no. But what was the thing I forgot to check for? Did I write less than or equal to here, or did I write less than or equal to with the subscript p? I got to make sure this reduction takes polynomial time. Because if it takes too long, then this is not a valid polytime reduction. So does this take polynomial time? Oh, well, we don't know if the clique or independent set does, but I'm just given an instance. I'm not checking for cliques. I'm not checking for independent sets. I'm just checking, I'm just taking a graph and doing something to it. That's all I'm doing. Well, I just got to make sure it's polytime. So why is it polytime? Right. So I'm only doing a constant amount of work per edge. Right. So I just check if it was there, then I make sure it wasn't there in the complement. If it isn't there, then I make sure it is. So it's linear in terms of the size of the graph, in terms of the size of the graph. That's what's key here. So it's linear in terms of the size of the graph. That's clearly polynomial time. So therefore, this is a polytime reduction. Okay? What about the other direction? Like, I have an instance of independent set and I want to make an instance of clique.
Are you doing essentially the same thing?
Essentially the same thing, right? Right? So I can just do a complement again to get back to the original graph, which obviously would preserve the answer. So therefore, we have the other direction too, by just undoing the reduction. So what can we conclude from this? From these two statements?
That it only takes a polynomial?
Well, either both have polytime algorithms or neither do. Because if one of them had a polytime algorithm, then we can just apply a reduction to get to that easy problem. So therefore, what's the term that I came up with for these two problems?
Non-deterministic.
Not that. Polytime equivalent, yes, exactly. So we call Clique and Independent Set polytime equivalent. So they're either both NP or they're both not NP, right? And we don't know the answer to that question, but we believe that they're not NP, just as a little teaser. So any questions on Clique and Independent Set? Okay. So now we're going to talk about a little bit of a different problem, so called vertex cover. So what is vertex cover? It's basically choosing some subset of vertices in the graph such that every edge touches one of those subset of vertices, right? So if I say I have this big graph and I pick 100 vertices, let's say, and every edge touches one of those 100 vertices, then I call that 100 vertex subset a vertex cover, because it covers the entire graph. It covers all the vertices. No, not all the vertices. It covers all the edges. Okay? So that's what we call a vertex cover. And so I define it this way. I define it in terms of a graph G and also an integer k. G is a graph with a vertex cover of size at most k. So why did I write at most k here? What's a really easy vertex cover for any graph? Well, think about it. Every single edge touches at least one vertex. So what can I do? Just pick every vertex, right? So what if I phrase this in terms of at least k? So the answer would always be yes, right? Because I can just let k be n, and I just found a vertex cover, right? So it's an easy question to do at least k here, but at most k is different because I need to iterate through all possible choices of k vertices to make sure that it is a vertex cover first. But I don't know how to do that easily and efficiently yet. Okay? So now what we want to do is we want to show at least one direction here, that vertex cover reduces to independent set. So I want to get this graph G in integer k such that it has a vertex cover at most of size at most k, if and only if the whatever I would transform it to has an independent set of size at least some integer that I provide. Okay, and make sure it's a polytime reduction. So, well, think about it. Let's just say that we have some vertex cover, W. There always is a vertex cover, right? Because I could just pick every vertex. But let's just say that there is some vertex cover of G. I don't know how big it is. But think about it. If I just remove those vertices, right? Then if I just remove those vertices, then everything else is an independent set. Why? Because every single edge touched one of those vertices in this set W. So if I remove everything, then I have a whole bunch of isolated vertices. So I just made an independent set, right? So this is a reduction, right? So if I have a vertical bar V vertex graph, what I do is I just ask if there is a vertex cover of size at most k, then I can just ask the question, if I can remove any of the k vertices to get an independent set of all the other vertices, right? If there's a way for me to remove k vertices such that everything else is an isolated vertex, then I have an independent set. Because that's what an independent set is. So I can actually do this reduction, right? Just by this careful observation that if I have a vertex cover, then if I remove all those vertices in the vertex cover, then I have a whole bunch of isolated vertices, which is an independent set, right? All those other vertices are part of this independent set, so I can include them all. So all I need to do is, I actually don't even need to modify the graph at all, right? all I need to do is just ask the question whether it has an independent set of size at least this number, which is just removing some subset of k vertices. Remember, I don't have to actually do the computation of figuring out which k vertices this is. I'm just transforming a graph in an integer into another graph in another integer. That's all I'm doing, right? So this clearly is polytime, right? It's just subtraction of an integer, of two integers. So therefore, we have vertex cover reduces the independent set, and I'll leave it as an exercise to prove the other direction. So you can actually produce from an instance of independent set into an instance of vertex cover. So therefore, these two problems are polytime equivalent. Oh wait, we just talked about clique and independent set being equivalent. And then we just said that independent set and vertex cover are equivalent. So now we have 3 equivalent problems. Pretty nice. Now it starts to seem a little more apparent that maybe there is some kind of notion of hardest problem in NP, right? There are a whole bunch of hard problems in NP for which we do not know if there's an efficient algorithm for. Okay? So any questions on vertex cover before we get into the crux of this stuff? So what we're going to do now, briefly, I think, briefly, is what's called NP-Completeness. So how many of you have heard of NP-Completeness? So do you remember what this corresponds to?
It's very familiar. I can't. It's on the tip of my tongue, but I don't quite. I can't.
We'll get to it. So it's this notion of we can stick it onto this problem to mean that we believe this problem is the hardest problem in NP. But we'll formalize it in a second. But the intuitive idea is that this is complete for NP. This is the hardest problem in NP with respect to some metric. So now we have some idea whether a problem has a polytime solution or does not, right? Either these 3 problems we just talked about either have polytime solutions or do not have polytime solutions, right? All 3 do or all 3 don't. We just want to show that a certain problem is difficult. So what did we talk about with respect to a problem being hard, right? We talked about a problem being hard if it turns out if there were an efficient algorithm for it, then everything else becomes easy, right? So essentially, if this problem were easy, then I can transform any problem that I want into this problem, right? Because if it were easy, then everything else becomes easy, and therefore, whatever problem I considered before, that becomes easy because I can just transform it into this formally hard problem. Okay? So hard means here that no matter what problem I consider, I can transform it into this problem, right? And this hard problem means that it's the hardest one in NP. So if we can solve it, we can solve any other problem. And by solve it here, I actually mean solve efficiently. Of course, we can solve any NP complete problem, but it will take a long time. So we can reduce every problem to this problem, solve whatever this hard problem is, which corresponds to a solution for the original one. So what is this transforming called? We just did 2 of them. A reduction, yeah. So it's essentially a polytime reduction from any problem to this hard problem. And so now we're really finally able to understand what NP-completeness is. So what is NP-complete? We call a problem NP-hard if for every problem in NP, we can reduce it to this problem that we call NP-hard, right? So this does not mean that it's NP-complete. An amazing number of people in the literature and published papers establish that some problem is NP-hard, even though it might not even be NP-hard, or is NP-complete, even if it's not even NP-hard. So we call a problem NP-hard if we can transform any problem we want in NP to this problem. right? So this really is the hardest problem, but it's not an NP yet. So we call a problem NP-complete if it's in NP and it's NP hard. So there are NP hard problems that we'll see later on that we don't even have an algorithm for. They're NP hard, but we don't have an algorithm to do them. Provably, there's no algorithm. But so NP hard can go as hard as you want, but NP complete means you stick in the NP class, and it's the hardest problem in this class. And there's some notions of completeness for harder classes of languages, for easier ones, but we're going to stick with NP complete. So this is a famous picture that shows two possibilities, right? We don't know if P is equal to NP, right? Oh, yeah, we don't know if they're equal, so we'll look at all possibilities. So if they are equal, then it collapses down to P and NP are being the same. And so therefore, since NP complete consists of problems in NP, since P equals NP, then they're all the same, right? But if they're different, then we have some separation. These NP complete problems are outside P. Right, so if there is a separation, then we have some problems that are outside of P, but are also in NP. And it also turns out that there are some problems in between that are not NP complete or in P, if they are different. But we won't go over that. So any question on NP completeness? Okay. Let's see. So the next problem will take roughly 30-40 minutes, so I'm going to stop there, and I'll see you next week.